All right, chapter 18 is on refraction and lenses. So first we'll look at the refraction of light. So what light does when it enters a new medium is it bends and changes angles. And I'll show you kind of why that is in a second. But here's what it would look like in real life. You know, you put a prism or a different surface that's opaque, translucent. And light can go through this, and then you can see that the image is off and bends. You see this through water maybe, but light does bend and then gives us like a virtual image. All right, so Snell's law then is the mathematical relationship that we're going to use to discuss that bending of light. N is the index of refraction, which is, well, I'll tell you what that is in a second. But for now, I'm going to give you those values in the table. So I'll give you all those values. So the index of refraction in a vacuum is 1. Air is then 1.003. Water is 1.33, and so on. So I'll have to give you these indices of refractions in the context of a problem. Theta is the angle before, and theta 2 is the angle after it refracts into the second medium. So let's do a quick example then real quick. Let's say that a light beam hits a sheet of crown glass at an angle of 30 degrees. So this is 30 degrees right here. At what angle is the light refracted? So what we're going to do is n1 sine of theta 1, which is Snell's law, equals n2 sine of theta 2. Really simple. Now we do need to know the indices of refraction, so we're going into crown glass, and I'm assuming then we're coming from air. So we'll use air for N1. That index of refraction from this table up here is 1.0003. And then we have the sine of the first angle, which we said was 30 degrees, equals N2, which is crown glass, which is 1.52, times the sine of theta 2. Now what we're solving is for this right here, theta 2, so we would divide both sides by 1.52. And we would take the inverse sine of this number right here. So I'll just write that like it is. And that gives us 19.2 degrees approximately. So it looks like this angle's smaller than it is because light hits it and light slows down and then bends to a smaller angle of about 19.2 degrees. So here's why that is, I guess. Why that is because waves behave in this manner where they change speeds based on the medium that they're in. So what happens is the wave front here, you can tell, hits the new medium first, and that portion of the wave slows down while this portion over here is still going faster. And so what happens is the wave kind of changes directions, as you can see. All right, so the next thing is, what is n? The index of refraction n, all it is a ratio of the speed of light to the speed in the medium. So all it is the ratio of the speed of light to the speed of that light in a specific medium. Speed of light in a vacuum to speed in whatever medium you're talking about. All right, so here's some application then of what happens then. Let's say we have a laser pointer and we're shining it in from underwater. What happens is if you're at the right angle, some of the light is going to escape the water and some of the light is going to reflect off the surface of the water. So you're going to get the light ray breaking up into two different light rays. If you reach the right angle, it's called the critical angle. What happens is some of the light reflects off the surface and some of the light reflects directly along the surface, parallel to the surface of the water. And then what happens after that critical angle, so if you move the angle up here more, all the light gets reflected off the surface of the water and none of it escapes. Okay, that's called the critical angle of internal reflection, and we have a math formula for that as well. All it is a ratio of the two indices of refractions. The sine of the critical angle equals that ratio. Okay, another application of refraction is with mirages. So here's what a mirage looks like. I'm sure you've seen them before. And why it happens is the best picture I can give you is this last one right here. What happens is you have wave fronts here, and it's the air is moving faster, or the light is moving faster through warmer air, and it's moving slower up here where the air's a little bit cooler. And so you have this refraction of this bending of the light. And so what your eye perceives is at the very end here, your brain detects the direction that this light's coming from as down here. So what you see is a virtual image down below the road. All right, so let's look at the dispersion of light then. We already know that if you take white light and you shine it at a prism, it breaks into its individual colors because of the fact that these different frequencies travel at different speeds through the medium. So what happens is you get this refraction of the different colors, and you get Roy G. Biv from that. And this is how rainbows are actually formed as well, because this same thing happens within a water droplet. You have this separation of the colors, and because your eye's seeing basically then the red from this one, the green from this water droplet, and the blue from this water droplet. So what you basically see is the separation of colors. You see a rainbow. Another application of this would be like when the sun goes down, you see it to be more red, and the reason why is because this bending of light. The reason why it appears red by the horizon is because there's a bunch of air here, and that resonates the red frequency, allows the red frequency of light, but scatters all the blue out. So what ends up making it to you is the red. But I guess the better application of what we just said here would be sometimes you see a green flash at the end, which happens after the sun's already down, and from the refraction of green light that actually comes and what you see at the very end. It's a little hard to see. You might want to pull up a YouTube video and watch like a slow motion of it happening, but it does happen. So the next thing is convex and concave lenses. We have a thin lens equation, kind of like our mirror equation, which gives us a relationship between focal point of the lenses and the distance to the image and the distance to the objects. Same as magnification. Here's what happens as light travels through like a convex lens, for example. It does converge to a specific point. If it goes through a concave lens, it does diverge, as you can see here. And once again, all this information is summarized for you, and I put all that information on the notes, or on the formula sheet. So it's not stuff you have to memorize. Everything is on here. So, here's another example. If you have a magnifying glass, which would be a convex lens, all the light diverges to a specific point, and all that energy then is all focused on one specific point, which can be very hot. I'm sure you remember experimenting with something like that when you were a kid. So an example would be that if we place an object in front of a lens, you can see these rays diverge to a point down here, which means the image is going to be smaller and it's going to be inverted. Okay, and that's all information, once again, that if we place the object at a distance greater than twice the focal length, that was a convex lens. So we're placing the object greater than twice the focal length, so we're talking about this column. We have a reduced and inverted real image then, just like we saw right here. All right, so let's do an example then. Let's say an object is placed 32 centimeters from the convex lens. So that's the distance of the object, is 32. And it gives us the focal length of the object as well, which is 8 centimeters. The question is, where is the image? So we're going to use our thin lens equation on the formula sheet, which is 1 over distance of the image plus 1 over distance of the object, in which case we have 1 over 8 equals 1 over d sub I, which is what we're looking for, 1 over 32. Subtract 1 over 32 from both sides, and you get 1 over distance of the image. We can do this one by hand because we can multiply top and bottom of this one by 4 in order to get a common denominator. And then we could say, okay, well that's 3 over 32, so flip it, 32 over 3 equals distance of the image. So the first answer is 32 over 3 centimeters on the other side here. The next question then, it says, if the object is 3 centimeters high, how tall is the object? So we have the height of the object is 3. Question is, what is the height of the image? We're going to use our magnification equation, which is height of the image over height of the object equals distance of the image divided by distance of the object. So we have everything we need. Just go ahead and plug in 3 right here for height of the object. Distance of the object was 32. Distance of the image was 32 over 3. Now dividing by 32 is the same as multiplying by 1 over 32, so I'll move that to the top, in which case the 32's cancel. We get height of the image over 3 equals, there's a 3 in the bottom, so that'd be 1/3. And then we can multiply both sides by 3. So the height of the image is -1, which means it's inverted. So it'd be, we can say 1 centimeter for height of the image. and obviously it's below the x-axis or whatever, below the focal axis. So we say that's negative. So the orientation then is going to be opposite orientation, being that it's flipped around. Here's a couple more examples then with a convex lens. It turns out if you place the object closer, you can actually get a virtual image behind the actual object. And that's once again on the formula sheet. And if you place the object really far away, you can get a virtual image in front of the concave lens, if you have a concave lens. Chromatic aberration is something that happens with lenses too. As you can see, if this lens isn't the perfect shape, then what happens is some of these different colors are separated, so you get this chromatic aberration of the different colors meeting at different points. So an achromatic lens would be when they all meet at the same point. Okay, this does have tons of application. Obviously, one of the big ones is for our eyes, because our eyes are convex lenses. So what's happening is light is supposed to come in parallel, and it's supposed to reflect and hit back on the retina, refract, I should say. And obviously, when your eye loses its shape, what can happen is that light can come in, and when it refracts, it meets at a point like behind the retina, which causes nearsightedness. So the shape of this convex lens is important, and that's what LASIK surgery obviously corrects. Actually, I believe LASIK surgery actually corrects the cornea, shape of the cornea, to add to some of that refraction to make up for it. But nonetheless, I know there are some surgeries that actually replace this lens as well. Okay, so then another type of telescope. I showed you the other day about a telescope with concave mirrors. You can also use lenses like this. Convex lenses, if you use 2 of those, you can also achieve a good zoom as well. So this would be a refracting telescope. Binoculars typically work like this, where you have an objective convex lens, 2 prisms, and then a convex lens, and then an eyepiece. And obviously that is going to zoom in the object as well. Obviously cameras have a series of mirrors right here with lenses, and then another lens here. And microscopes are also another application. All right, let's start the homework, and hopefully this helps.